We're now getting into functions, and we're going to look at, in this chapter, graphing functions using techniques of transformations to graph functions. But first, we need to figure out what a function means, and that's what we're going to be talking about in this section. And so after I talk through and give you a lecture on this section, you should be able to describe what a relation is. You should be able to determine whether a relation represents a function or not. You should be able to use function notation and find the value of a function. You should be able to find the difference quotient of a function. Number 5 should be on a different line. 5, you should be able to find the domain of a function defined by an equation, and then form the sum, difference, product, and quotient of two functions. So a relation is between two sets, and it's a collection of ordered pairs containing one object from each set. So the ordered pair XY would be considered a relation. If the object X is from the first set and the object Y is from the second set, then the objects are said to be related if the ordered pair XY is in the relation. Okay, so what does it mean for a relation to be a function? In order to be a function, a relation is a set of inputs. So for every X value that we put in to a set of possible outputs, your Y values, or each input is related to exactly one output. So every input or every X value in the domain corresponds to exactly one output, which is the Y value, which is our range. So in the range. So if we have one X value that maps and gives us more than one Y value, then it's not a function. So let's look at some examples and see if the following is a function or not. Okay, so for our first example, we're going to determine whether the equation defines Y as a function of X. And we have Y is equal to X squared minus 2X. So we want to see if for every X value, is that giving us back one Y value or more than one Y value? If it's only going to give us back one value for every X, then it's a function. And so a way that we can start doing this is actually just starting to find points and see if it looks like we're going to get back more than 1 point for every X. So for instance, if I plugged in 0, right, wherever I saw an X, I would get 0 squared minus 2 times 0, which is 0. Okay, so there's one X value, it spits out one Y value. So that example, or at least that number, it would say, yes, that's a function. So I would try to think to myself, is there anything that I could plug in here? So like if I plug in 1, is there anything I can plug in here that would give me back more than one Y value? And in this case, actually, no. If I plug in 1, I would get 1 squared minus 2 times 1. Well, 1 squared is 1 minus 2 times 1, which is minus 2. So 1 minus 2 is negative 1. If I plugged in negative 1, I would get negative 1 squared, which is positive 1, minus 2 times negative 1, so that's really plus 2. So 1 plus 2 is 3. So there's nothing that I can think of that if I plug in a value for X, I would get more than one Y value. And so I can see that this is going to be a function. What about the example if we had y squared is equal to 3x minus 4? And we want to know, is this a function or not? If your equation is not in the form of y equals, it's probably best that you put it in that form, and then you can it'd be easier to see if it's a function or not. And so notice this is y squared equals. We can get rid of that y squared by taking the square root of both sides. But recall, when we take the square root of both sides of an equation, we have to put in that plus or minus. So we have the square root of y squared. This is equal to plus or minus the square root of the quantity 3x minus 4. So I get y is plus or minus the square root of 3x minus 4. So in this case, I can tell if I plot a point, I'm possibly, if it's in my domain, I am going to get back more than one y value. Okay, well, first of all, we have to think about our domain. And so domain, we're worried about this value, 3x minus 4. This has to be greater than or equal to 0 in order for that to spit out a real number. If I solve for x here, I get 3x has to be greater than or equal to 4, or x has to be greater than or equal to 4/3. Okay, so I know now when I'm choosing my x values, I wouldn't choose something smaller than 4/3. I was thinking of putting 0, but I noticed that that was going to give me an imaginary number, and 0 is smaller than 4/3. So how about let's plug in 2. If we go in here, we plug in 2 wherever we see an x, we're going to get back, this is plus or minus the square root of 3 times 2, which is 6, and then minus that 4. So 6 minus 4, we have a 2 underneath the radical. And so here is one example where one input gives us back 2 outputs. So this is not a function. Because one input corresponds to 2 outputs. So let's look at the following. 5x plus 7y is equal to 10. So again, we're looking at this and we want to see if this is a function or not. I notice that it's not in the form of y equals, but after that last chapter, I can tell that this is a line and it's actually in standard form. And if we think about a graph of a line, I know that a line other than vertical line is a function. But let's do what I just said. If it's not in the form of y equals, a lot of times it's easier to put it in the form y equals. So let's solve for y here. Let's subtract 5x on both sides. We would get 7y is equal to negative 5x plus 10. I could go through and divide everything through by 7. So every single term by 7. So I get y is equal to negative 5/7 times x plus 10/7. So again, if I'm starting to plot points, I don't see any value I can plug in for x that would give me back multiple values for y. For instance, if I plug in 0 for x, I get y is 10/7. If I plug in 1 for x, it's nice because these are common denominators. So if I plug in 1 for x, I get -5/7 plus 10/7, which is 5/7. So there's no case I can see that if I go in here and plug in a value for x, that I'm going to get more than one y value. So I can see that, yes, this is a function. So one more. What about y is equal to 2 over x minus 3? Okay, so I noticed that this is actually undefined. I know my value of x can never be 3 because that sets my denominator equal to 0. Other than that, I can plug in any value n for x. That would be in my domain. Again, if I start plotting points, I can't see any value of x in here that would give me back more than one value for y. So if I plug in 0 for x, I would get 2 over -3 or -2/3. If I plugged in 1 for x, I would get 2 over 1 minus 3 or 2 over -2, which is -1. So there's nothing that we can go in here and plug in for x that would give me back multiple values for y. If I plugged in -1, I would get 2 over -4, where that reduces to -1/2. So yes, this is a function. Maybe instead of an equation, you are given a set of ordered pairs of points, and looking at the set of points, would that relation be a function or not? So for instance, let's say you were given the following sets of points. So -2, 5 is 1 point in our set. -1, 3 is another point. 3, 7, and 4, 12. And it asks, determine whether the relation represents a function. For each function, let's state the domain and the range. Okay, so the domain in this case is our x value, and our range would be our y value. So when it's a point, I tend to like to map them. So our x values, let's just write them down. So -2, -1, 3, and 4. And then let's write down our y values. We got 5, 3, 7, and 12. And notice that -2 maps to 5. So that x value, -2, gives me back one y value. -1 gives me back the output of 3. The input of 3 gives me the output of 7. And the input of 4 gives me the output of 12. And so looking at this, I can see that every x value corresponds to one y value. And so, yes, this relation is a function. What if it was the set of points 2, 5, 3, 5, 4, 5, 5, 5. So again, we want to determine what the domain is, what the range is, and if this would relate to a function or not. And so our domain, notice our 2, 3, 4, and 5. And our range, only output that we get is 5. So 2 goes to 5, 3 goes to 5, 4 goes to 5, and 5 goes to 5. So by the definition, to be a function, every input corresponds to one output. So think to yourself, 2, how many values of y does that go to? Well, 2 only goes to one value of y, 5. Okay, so that's okay. 3, how many values of y does that go to? It only goes to one y value. So here, 1x corresponds to 1y. 4 goes to one y value, which is 5, and 5 goes to one y value, which is 5. Just happens that they're all going to the same y value, but by definition, it says every x value corresponds to exactly one y value. And so in this case, this is a function. Where if maybe it was flipped, instead, maybe x was always 5. So let's say 5, 2, 5, 3, 5, 4, and 5, 5. So this is a case where we only have one input of 5. Our range, our output, we would have 2, 3, 4, and 5. But our domain, 5, what's in that domain is going to more than one output. Okay, messy now. So this is not a function. Okay, so you should be able to, given an equation, find the domain of a function. Right, so there was a question. So it was a function because they all only have one output, and that was correct for this this second to last example. They corresponded, each number, x value corresponded to one x value, sorry, y value, where this one was not because one x value corresponded to more than one y value. When you're trying to find the domain, I always kind of look for my trouble spots because the domain are all real numbers that we can plug into a function and get back a real number. So finding the domain, look for your trouble spots. And exclude these. Okay, so what are things that would give us trouble when we're looking at some equation or some function? Well, remember, we can't have 0 in the denominator. So things that set the denominator equal 0. So values that set the denominator equal 0. those would give us problems and we need to exclude them. We can't have a negative underneath a even powered radical. So negative values which gives a negative number under an even powered radical. If n is odd, then we're not going to have any problems. We can have a negative number underneath that radical. But these are values that we need to be aware of, and these are values that we would have to exclude from the domain. And so if they just give us an equation and ask us to find the domain, we see if there's any trouble spots. Are there any variables down in that denominator? If so, we have to figure out what sets it equal to 0. Or do we have any radicals in our equation? And if so, we're going to have to see if it's an even powered and set what's underneath the radical, which is called the radicand, greater than or equal to 0 if it's not in the denominator. So let's say that we're given that f of x is equal to 2x plus 3. So instead of writing this as y equals 2x plus 3, f of x is just another way of saying y, and that's just function notation. And we want to find the domain of this. Well, it doesn't have any radicals and it doesn't have any variables in the denominator. And so my domain is going to be all real numbers. And so my domain in this case, if I put it in interval notation, is negative infinity to infinity. I can plug in any real number for x and I would get back a real number for y. So before we move on to look at more examples, let's say it wanted us to find f of -2. So we had f parentheses -2. So this wants us to find y when x equals -2. So all we're doing, right, is we're going in and we're plugging in -2 wherever we see an x. So we have 2 parentheses, and replace it with -2 plus 3. So simplify, order of operations, multiplication comes first. We get -4 plus 3, which is -1. Okay, so our domain is all real numbers. Let's go a little further. Let's say it didn't ask us to find f of a number. Let's say it asked us to find f of an expression, maybe x plus h. So what this tells me to do is I'm going to go to my function f of x. Wherever I see an x, let's just put in a parentheses for now. So here we have 2. I see an x, so I'm going to put parentheses big enough to put in x plus h plus 3. I can leave it like this, or I can simplify. Let's distribute our 2. So this is 2x plus 2h plus 3. These are not like terms, and that's as far as I can take it. Let's say it wanted you to, so I'm going to say that was A, this is B, this is C. Let's say it says find negative f of x. All that's telling you to do is multiply my f of x function by -1. So this would be negative of what my f of x function was, which is 2x plus 3. So this is like distributing a -1 inside my brackets. So this would give me negative 2x minus 3. And go a little bit further. And let's say it wants us to find f of x plus h minus f of x, and then it wants us to put it all over h. We actually did part of this already. Well, our f of x plus h, we found in part C. This was 2x plus 2h. Let's write that in there. So this is equal to 2x plus 2h plus 3. And then it wanted us to look at minus our f of x. Minus f of x we already found. That was minus 2x minus 3. And then it tells us to put this whole thing over h. So let's simplify that. We can combine like terms. I have a 2x minus a 2x cancels. I have 2h. And then I have a positive 3 minus a 3 cancels. And this is all over h. So 2h over h, which is equal to 2. What we had just done is called the difference quotient. Okay, so the difference quotient and you'll be using this once you get into calculus a lot. So this is actually part of our formal definition of what a derivative is. And this says a difference quotient of f of x is f of x plus h minus f of x all over h. Let me show you where it came from. Let's say we have 2 points. Let's call one x f of x. And let's call it, let's say our x value is x plus h. Then I know my y value I can represent as f of x plus h. So let's find the slope of the 2 points. Okay, so recall the slope is our change in our y value. So our change in our y value. So our second point, f of x plus h, minus the y value of our first point, f of x, all over this change in my x value. So x plus h minus x. Notice if I simplify my denominator, I have like terms x minus x, so those cancel. I can't simplify my numerator, so I'm just going to leave it as f of x plus h minus f of x all over h. Technically, this is going to help us to be able to find the slope on any curve that exists, where the slope exists, or the rate of change exists. So far, we've only been able to find the slope at a particular point on a line. But what if it wasn't a line that we're looking at? Maybe we are looking at some curve. It could be a parabola. And we wanted to find the slope at this value right here. So let's just say that that is some value x right there. Well, if I wanted to find that slope right there, I could do that, or I could get accurate by choosing points closer and closer to this point x. So if I chose something out here, I could get some sort of an estimate on what that slope is by finding the slope between those 2 points. But if I choose a point even closer, so maybe I choose a point right here. If I chose a point closer to x and I find the slope between those 2 points, I'm going to get even a better estimation of what that slope is. If I even chose it closer, I'm going to even get a better estimate of what that slope is at that particular point. So in calculus, what we're doing is we're actually limiting that distance, because what we're choosing that point to be is we're adding h to this x value. Okay, and so this would be the value of x plus h and f of x plus h. And so as that distance shrinks, as h goes closer and closer to 0, our points get closer and closer to the point that we were trying to find the slope. And that's where that difference quotient is coming from. So it's not a huge deal if you don't know that, but that's kind of where we're stemming from and why this is so important to get down this difference quotient. Okay, so one more example of the difference quotient, and then we're going to have to stop for today. But we have f of x equals x squared plus 5x minus 1, and we want to find that difference quotient. So again, we want to look at what is f of x plus h minus f of x. And then we're going to put this all over h. And so if it helps you out to do this, do it in steps and then put it together. So if we first wanted to look at f of x plus h, that's telling me I'm going to go back in, and wherever I see an x in my function f of x, I'm going to replace that with the expression x plus h. So let's just go in, put parentheses wherever we see an x. So I have parentheses squared plus 5 parentheses minus 1. So let's go in now and plug in x plus h inside those parentheses. So I have x plus h quantity squared plus 5 times the quantity x plus h minus 1. We're going to have to expand this. So I have to multiply x plus h times x plus h. I'm going to have to just distribute my 5. So this would give me plus 5x plus 5h and minus 1. So if I distribute x plus h times x plus h and combine like terms for time's sake, I have x squared plus 2xh plus h squared. If I had multiplied that out and combined like terms, so plus 5x plus 5h minus 1. Okay, so that is just my f of x plus h value. So let's plug that in there. So that is x squared plus 2xh plus h squared plus 5x plus 5h minus 1. minus f of x. Just going to put it in here. So this is minus, be careful, you have to put parentheses around the whole quantity of f of x if it's more than one term, which this is. So minus the whole quantity x squared plus 5x minus 1 all over h. So if I distribute my negative sign, I got to bring everything else down. So x squared plus 2xh plus h squared plus 5x plus 5h minus 1. Distributing my negative 1, I get negative x squared minus 5x plus 1. And this is all over our h value. So notice x squared minus x squared cancels, 5x minus 5x cancels, a negative 1 plus 1 cancels. So if you do this right, a lot of times, a lot of things are going to cancel out. And notice that in our numerator, all we're left with is that 2xh plus an h squared plus a 5h all over h. Notice this numerator, we can factor out an h. So if we pull out an h from that numerator, you're left with 2x plus h plus 5 all over h. And so now we can simplify, the h's cancel, and we're left with the 2x plus h plus 5. And that is the difference quotient of the function x squared plus 5x minus 1. Okay, so we're going to stop there. We didn't finish this first section in chapter 3. We'll continue with that on Thursday.